In this lesson, we'll look at another quadratic word problem where we're dealing with a maximization problem. So in this problem, we're asked, or we're told, a rectangular lot is bound on one side of a river and on the other three sides by a total of 100 meters of fencing. Determine the area of the largest possible lot as well as the dimensions. So here I've drawn out a little diagram for this problem. You see that we have three sides that are enclosed by fencing, and the other side is just a river. So we don't need fencing along that side of the lot. So our objective here is to try to maximize the area of the lot. And to do so, we're going to have to come up with this is going to be a quadratic expression, and we're going to have to maximize this quadratic expression. So the first thing that we're going to do is we're going to come up with an expression for the area of the lot in terms of the length and the width. So we'll say that that's the length, and this is the width. And we know that because we have a total of 100 meters of fencing and we're only using fencing on these three sides, we know that L plus 2W, which is the amount of fencing that we're using on these three sides, has to be equivalent to 100 meters of fencing total. So now I can rewrite the length in terms of the width. And I can rearrange this equation. If I subtract 2W from both sides of this equation, I get L is equal to 100 minus 2W. Now, if I come up with an expression for the area of the lot, I know that the area of the lot has to be equivalent to the length times the width. And if I rewrite the area if I rewrite the length in terms of 100 minus 2W, I get that my area is equivalent to 100 minus 2W times W, which is equivalent to, well, now I can expand this and I get an equation in standard form. So I get 100W minus 2W squared is equivalent to the area. Now I want to try to maximize this area to get the largest possible lot. And to do so, I'm going to complete the square on this expression. So first thing that I'm going to do is I'm going to rewrite this expression in descending order. So I've got minus 2W squared plus 100W. And then the next step in completing the square is to factor out if there's a coefficient in front of the squared term. I'm going to common factor that coefficient out of the first two terms. And here there's no constant term. But if there were a constant term, I would leave that term out. I would not common factor negative 2W out of the constant term. So now I get negative 2 times W squared minus 100 divided by 2W. 100 divided by 2W is negative 50. So I get minus 50W. And the next step in the procedure is to divide negative 50 by 2, square it, and then add it and subtract it. And I'm doing this so that I get a perfect square trinomial here. So I do minus 2W squared minus 50W. If I divide negative 50 by 2, I get, well, let's see here, negative 50 divided by 2 squared is equivalent to 225. Or, shoot, whoops, it's actually 625. Because it's negative 25 squared is 625. So I get plus 625 minus 625. And this is equivalent to, now I can move the negative 625 outside of the bracket by multiplying it by negative 2. And I get W squared minus 50W plus 625 plus, well, 625 times 2 is 1,250, which is equivalent to, now I have a perfect square trinomial here, and I can factor this to W minus 25 squared plus 1,250. And this has vertex located at 25, 1,250, and the vertical value of this of the vertex represents the maximum area, and the width value here represents the width that maximizes the area. So therefore, the maximum area of the lot is 1,250 meters squared. And to determine the dimensions, well, I already know that the width that maximizes the area of the lot is 25 meters. So to calculate the length of the lot that maximizes the area, I'm going to do L is equivalent to 100 minus 2 times W, which is 25. So I get 100 minus 2 times 25. 100 minus, 2 times 25 is 50. So I get 100 minus 50 gives me 50. So therefore, the area of the lot is 1,250 meters squared. And the dimensions that maximize the lot are 50 meters by 20 meters. That concludes this video, and we'll see you in the next lesson.